we are going to learn what do you mean by partially ordered set or a POSET. Suppose we have any relation R that is on the set S. That relation is called as the partially ordered or partial ordered if it is a reflexive, antisymmetric, transitive. Reflexive means every element is related to itself, means we have the ordered pair of the form this in a relation. Whereas antisymmetric means we can take such elements in a relation, and if we have the ordered pair AB as a part of a relation, then reverse ordered pair is not allowed in a relation. Moreover, the transitive relation means if ordered pair AB is a part of relation as well as ordered pair BC is a part of relation, so there must be an ordered pair of the form AC in a relation. If all these three conditions are valid, then we call it R as partially ordered or partial ordered. If we have the relation that is partially ordered on the set S, we call it as the POSET, that is partially ordered set. It is represented by this form where this S represents the set and R is the relation on the set S. In this case, the members of S are called as the elements of the POSET. Let's understand this partial ordered set with the help of example. Suppose we have the relation on the set of people. We are saying that X is related with Y, means the ordered pair XY is a part of a relation if and only if X and Y are people and X is older than Y. Whether this R relation is a partial ordering or not. So what we need to check? We need to check these three conditions. Let's start from the transitivity. Now suppose X is older than Y and Y is older than Z. Can we say that X is older than Z? Yes. So it means this is applicable for all set of people that hold these two conditions. So obviously X is older than Z. Now whether this is an antisymmetric means if they are different persons, X is older than Y. Can we say that Y is older than X? No. So clearly reverse form is not applicable in this case. It means it is an antisymmetric as well. Now what about the reflexive? Reflexive means we have the ordered pair of this form, means every element is related to itself. Now here the relation is X is older than Y. So we will replace Y with X. So can we say that X is older than X? Means X is older than itself? No. So X cannot be older than itself. It means it is not a reflexive relation. Thus we can conclude R is not a partially ordering. Let's take the next example. In this case, we need to identify which of the following is a POSET. So here first we have taken the set and then relation is defined on the set S. So this Z indicates that it is a set of integer, where this indicates that it is a set of positive integer, and PS means power set of S. Let's cover one by one. So here we need to check whether the set of integer with the relation less than equal to forms the POSET or not. Ultimately, we need to check the three things: that whether the relation is reflexive on set of integer, antisymmetric on a set of integer, relation is transitive on the set of integer. If yes, we can conclude that it is a POSET. And same thing we need to do for the rest of the cases. Starting with the first case, we need to check whether less than equal to relation on the set of integers is reflexive or not. Reflexive means every element is related to itself. So here, whether every element is less than equal to itself? Yes. So it means this relation on set of integer is reflexive. Now, for the antisymmetric, how to check this one? First step is we will remove the equality. Why? Because in the antisymmetric, we can take such type of ordered pair in a relation. We just need to check when A is not is equal to B. And if AB is a part of relation, then reverse should not be there. Now, if A is not is equal to B, means we need to remove the equality. In that case, if AB is a part of relation, so surely A is less than B. Whether this implies yes. If the statement is true for every case, it means it is a antisymmetric. What about the transitive? Whether this relation is transitive on the set of integer means if A is less than equal to B, B is less than equal to C. Can we conclude A is less than equal to C? Yes. As the relation is reflexive, antisymmetric, transitive, so we can conclude yes, this represents the POSET, that is a partially ordered set. Similarly, check for the next case whether this is a reflexive. So we need to check whether every element is greater than or equal to itself. Yes. Now for the antisymmetric, A is not is equal to B, and if AB is a part of relation means in this case it will hold the condition that A is strictly greater than B. Whether this implies B is not greater than A? Yes. So it means it is an antisymmetric. What about the transitivity? If A is greater than or equal to B, B is greater than or equal to C, can we say that A is greater than or equal to C? Yes. This implies this is also a POSET. Now check for the next case when we have the set of integer and this represents the divide relation. Divide relation means if A divides B means B by A is equal to some integer, means B is divisible by A. Like 2 divides 16 but 16 does not divide 2. So here we need to check whether this is a reflexive on the set of integer, whether every element divides itself from this set of integer. No. Every element divides itself except 0. So 0 does not divide itself, due to which this is not a reflexive and hence we can conclude it is not a POSET. Now before moving to the next case, let's check it for the knowledge whether this is an antisymmetric relation or not. If we say that A not is equal to B and AB is a part of relation, if A divides B, can we say that B does not divide A always? No. Why not? You can take the case of 2 minus 2. 2 divides minus 2 as well as minus 2 divides 2. So this is not possible in each and every case. If the number is divided by its negative 1, reverse case is possible. So it means it is also not an antisymmetric relation. Now what about the transitivity? If A divides B, B divides C, whether we can say that A always divides C? Yes. So this is always a transitive but not a reflexive and antisymmetric relation on the set of integers, due to which this is not the POSET. Now what about the next case? Set of integer, we are taking the elements that are equal, means we are taking the elements of the form 1 1, 2 2 and so on. Now whether this is a reflexive relation, whether every element is equal to itself? Yes. For antisymmetric, we are taking A is not is equal to B. In this case, we don't have such cases. But we know that in antisymmetric, such ordered pairs are allowed. So there is no problem in this case as it is an antisymmetric relation as well. For transitivity, if A is equal to B and B is equal to C, can we say that A is equal to C? Yes. So it means it is a transitive, hence it is a POSET as well. For the next case, set of integer with less than form. Whether this defines the reflexive relation on the set of integer, whether every element is less than itself, no. So as it is not a reflexive, so we can say that it is not a POSET. What about the next case? Whether this relation is reflexive on the set of integer, whether every integer is greater than itself, no. So it means it is not a POSET. Now what about the G part? Here we have taken the set of positive integer and divide relation. Now whether every element divides itself? Yes, because we have removed the 0 from here. Set of positive integer means we have started the set from 1, 2, 3 and so on. So 0 is not the part of this one. So it means every integer divides itself. Hence the divider relation is reflexive on the set of positive integer. Now whether this is an antisymmetric, for A is not is equal to B, if AB is a part of relation, means if A divides B, can we say that B does not divide A in this case? In the previous case, we are taking the pair as positive negative or negative positive. Now in this case, we are just dealing with the positive integer, not with the negative integer. So yes, this case is now applicable. Now what about the transitive? If A divides B and B divides C, whether A divides C always? Yes. This implies set of positive integer with the relation divide is POSET. The last part we have the power set of S. Power set means it is a collection of all subsets of S. Suppose we have any set that contains the two elements AB. So what is a power set in this case? Power set in this case is singleton set A, singleton set B and AB. Also there exists an element phi because phi is a subset of all these sets. So this is called as a power set of the given set S. Now we have taken this as the subset. We need to identify whether this is a POSET or a not. So first check for the reflexive. Reflexive means every set is the subset of itself. Yes. For the antisymmetric, if the sets are not same, means if set A is not is equal to the set B. If A is a subset of B, now it is a properly contained in B. Can we say that B is properly contained in A? No. Even in antisymmetric, we say reverse should not be there, and in this case, B never be a contained in a A. It means it is an antisymmetric. Now, for the transitivity, if A is a subset of B and B is contained in a set C, can we conclude that A is properly contained in a C? Yes. So it means it is a reflexive, antisymmetric, transitive and hence it is a POSET. So remember that set of integer with less than equal to and greater than equal to as well as equality relation defines the POSET. Moreover, set of positive integer with divider relation and power set with subset are the POSETs. Also note that the notation this is used to denote if any ordered pair is a part of a relation in arbitrary POSET this. What does it mean? Means generally we are representing a POSET where S is stands for the set and R stands for the relation. But sometimes rather than writing in this format, they are mentioning as set and this symbol. So this symbol indicates that this is the relation R which is reflexive, antisymmetric and transitive. Basically that is always a POSET. So whenever you have this symbol, always assume that with this relation on the set S, that defines the POSET. There is no need to figure out that is a reflexive, antisymmetric or transitive. We directly take it as a reflexive, antisymmetric and transitive relation. In the concept of POSET, we have three more important terms, that is comparable element. So in POSET, we can say that some elements are comparable. When we can say the elements are comparable? If either A is related to B or B is related to A. What does it mean? It says that either A is related to B with the relation R or B is related to A. Means either AB ordered pair is a part of relation or BA is a part of relation. So both cannot happen. Why? Because it is a POSET and in POSET relation is antisymmetric. Reverse ordered pair is not possible in the case of antisymmetric. So do not get confused with this one. This is not less than equal to. This is a symbol that indicates that this is always a POSET. For example, in POSET, when we say that set of positive integer with the divider relation, whether element 3 and 7 are comparable, means we just need to check whether 3 is related with 7 or 7 is related with 3. Now what is the relation in this case? Divide. So we need to check whether 3 divides 7 or 7 divides 3. So whether 3 divides 7? No. Whether 7 divides 3? No. So it means 3 and 7 are not comparable. Next we have are 8 and 64 comparable according to this POSET? So whether 8 divides 64? Yes. On the other hand, you can check it. 64 does not divide 8. So we just need one ordered pair in a part of a relation. If yes, so we can say that yes, 8 and 64 are comparable elements. Now when we say that two elements are not comparable, it means neither A is related with B nor B is related with A, and such elements are called as a incomparable. This symbol indicates that AB ordered pair is not the part of R and BA ordered pair is also not the part of R. Neither this nor this. So in that case, we say that elements are incomparable. So here we can say that 3 and 7 are incomparable elements. One more important term we have, that is the totally ordered set. Totally ordered means everything is in an ordered form. For that, first thing we need to think, what is the set? If the set with the relation is a POSET and every two element of that set are comparable, means we can compare each and every element from the set S, then it is called as a totally ordered set. And in this case, whatever the relation we have, that is called as a total ordered or linear order. And sometimes totally ordered set is called as the chain or the linear ordered set. As here we have done the many cases where we are getting a POSET, check it whether any POSET is called as a totally ordered set or a not. So the first POSET we have taken as this, whether set of integer with less than equal to is totally ordered set. How we need to check? Pick any two elements from this integer set. Let it be a 5 and 18. Can we compare them according to this relation? Yes. Whether that is possible for each and every case? Yes. So we can write in this case 1 is less than equal to 2, 2 is less than equal to 3, 3 is less than equal to 4. Continue this even from the negative side. Means we can compare each and every element as respect to this relation over the set of integer. It means this is the totally ordered set. Now what about this case? This is a POSET. Whether this is a totally ordered set? Yes. Again we can compare each and every element from this set over this relation. So it means yes, this is a totally ordered set. Now in this case, whether this is a totally ordered set? No. Why not? Pick any two elements. Let it be again 5 and 18. Can we say that 5 is equal to 18 because the relation is equal to? No. So it means this is not the totally ordered set. Every element is not comparable in this case. Moreover, no element in this set is comparable. Now what about the set of positive integer with a divider relation? Can we divide every two elements from this set? Take 5 and 18 again. Whether 5 divides 18? No. Whether 18 divides 5? No. So these two elements are not comparable. It means we cannot say that every element is comparable according to this relation in this set. It means this is again not a totally ordered set. Now what about this one? Whether this is a totally ordered set? So here we have taken a simple example. Here we can say that the set is a subset of B. No. Can we say that B is a subset of set A? No. It means these two elements are incomparable and hence the set is not a totally ordered set.